Welcome back, everyone. We are officially ready to move into our last set of guided notes, and that is Unit 8. So we'll be looking at the basics of functions and their graphs, how to define the domain and range, how to identify whether or not a relation is a function, that kind of thing. So we'll see how far in these guided notes we'll actually get today. Chances are we'll probably have to finish on Thursday. I don't imagine we'll be able to get through the whole thing today. All right. Welcome, welcome, welcome. This is fantastic. Let's get into the notes and see how far we can get. So the basics of functions and their graphs. So we're going to start off with the idea that a relation is any set of ordered pairs x and y, right? So you can literally have a list of ordered pairs and that would provide you with a relation. All of the x values in the ordered pairs are called the domain. They belong to the domain. All of your y values, they belong to the range. If ever you're like, oh wait, which is which again? Think x comes before y in the alphabet and d comes before r in the alphabet. So x before y, domain before range. X values make up the domain, y values make up the range. So if I had a relation here, a set of ordered pairs, we have 1, 6, 2, 6, 3, 8, 4, 9, and 5, 10, we want to determine the domain and range of each. Now we want to define the domain as a set of values, and we recall from our previous unit that to identify a set, we would use braces. So what we'll do in this case is we'll write down our braces, our set of braces, and we're simply going to list all of the values in our domain. So we have a 1, we have a 2, we have a 3, we have a 4, we have a 5. So in our domain, in order, we have 1, 2, 3, 4, 5. Those are the values that make up my domain. Easy enough, right? Next, we want to identify the values that make up the range. So again, we are going to note that we have a set of values, so we'll use braces. And let's take a look at our y values. We have a 6, an 8, a 9, and a 10. Now, the 6 ends up repeating, which is fine. We just won't write 6 twice in our set. We're going to list each value once. So a 6 appears in our range, an 8, a 9, and a 10. And it's as simple as that. Domain is all of our x values, range is all of our y values. If we happen to repeat any of those values, we only list it once. Okay, we're going to determine the domain and range for each of the following relations. I want you to notice that, for examples A, B, and C, they all look very different, correct? But it's always the same idea. Domain represents all of your x values, and the range represents all of your y values. So for part A, let's go ahead and set up the domain and range. I'm just going to use D and R for domain and range. Hopefully you're okay with that. As always, we have a set of numbers here. So for my domain, let's look at my x values. I have a 5, a -3, a 5, an 8, and a 7. Because I like listing these values from least to greatest, I'm going to start by writing the -3. After -3, we have 5. After 5, we have 7. And then lastly, we have 8. It's always helpful to double check. We have the 5, the -3, the 5, the 8, the 7. Good, they're all accounted for. Similarly, let's identify the values that are in our range. We have a 7, a 9, a -12, a -6, and a 3. Again, personal preference, I like to list them from least to greatest, so I'm going to start with -12. My next value in the range is a -6. After that, I have a +3, a +7, and a +9. Double check. 7, check. 9, yep. -12, yep. -6, perfect, and 3, perfect. We have listed all of the values in our domain and range. So we're going to continue with this same idea. For this second layout using this chart, the XY chart, I want you to notice that this refers to the ordered pair 3, 67, right? This first set of values refers to the ordered pair 367. If we were to write the next one, it would be 4, 75, and so on and so forth. So that is how this chart works. The great thing about it being written in this format is that it's going to be super easy for us to carefully write down all the values that are in our domain and our range. So all the values in our domain are 3, 4, 2, 6, 7, or in other words, 2, 3, 4, 6, 7. We're going to do the same thing for our range. Again, look at all the y values that you have listed here, and let's write them inside the set of braces. So we start with 59, 67, 75, 91, and 99. We should have 5 values here. We have 5 values here. Perfect. Nothing's repeating. Beautiful. We have the domain and the range. Now for our third example, we're following the same format, except this time we're just given ordered pairs. So what we may want to do first is identify what these points actually refer to. So for instance, if we start with this point, and we're also assuming that each mark is 1 unit. So for instance, -1, -2, -3, -4, we go down 2 units. So my first ordered pair is a -4, -2. Let's identify each of these ordered pairs. So I'm going to give you 30 seconds to write down each of these ordered pairs, starting now. All right, let's take a look. My ordered pair here refers to -2, 0. If we move to our point in quadrant 2, we have -2, 1, 2, 3, 4, 5. So it should be -2, 5. Let's move to our point in quadrant 4. We have over 2, down 1, so it's 2, -1. And now let's look at our points in quadrant 1. So we've got 1, 2, and we have 1, 2, 3, 1, 2, 3, we have 3, 3. So we first list all of the ordered pairs that are actually those points that are plotted on our graph. And now let's write out our domain and range. After this, it becomes a piece of cake, right? Your domain, those are your x values. They run from -4, -2, 1, 2, 3. Those are all of our values in order. -4, -2, 1, 2, and 3. Let's take a look at our values in the range. Always start from lowest to highest. So the lowest value is a -2, then -1, then 0, then 2, then 3, then 5. So -2, -1, 0, 2, 3, 5. Notice that as we move up, we're able to identify all the y values in increasing order. Beautiful. Let's turn the page when you're ready. A function is a relation that assigns to each element of its domain exactly one element in the range. That's very important. Recall that when we refer to the values in the domain, we're actually referring to the x values. And when we refer to the values in the range, we are referencing the y values. Okay, so in order for a relation to be a function, each x value has exactly one y value. Notice that it does not say the reverse. It does not say, and each y value has exactly one x value. That's actually really, really important for you to distinguish. So in other words, x values should appear only once in a set, but y values can appear more than once. So in order to be a function, each x can at most relate to one y value, not more than one. Okay? Let's take a look at what we mean by that. So we're going to determine whether a relation is a function. So I want you to look at all of these values. I want you to ask yourself, does any x value repeat? We have a 1, 6, a 2, 6, a 3, 8, a 4, 9. So in our domain, we have a 1, a 2, a 3, and a 4, and none of those numbers repeat. So because our answer is no, we can say this is a function. Okay, because the x values do not repeat, this is a function. Take a look at B. We have our ordered pairs 3, -1, 4, 6, 2, -8, 4, -5, 7, -1. I hope you notice right off the bat that our x value of 4 happens to be connected to both a 6 and a -5. So what that means is this is not a function, since our x value 4 repeats, meaning 4 is associated with both 6 and -5. That is a problem. That breaks the definition of being a function. Part C. We have 6, 1, 6, 2, 3, 8, 4, 9. Function or not a function? I'm hopeful that as you look at these ordered pairs, you would say, oh, wait a second. 6 shows up in 2 separate ordered pairs. So this must not be a function. Take a look at part D. We have our ordered pairs 367, 475, 259, 691, and 799. Notice each of our x coordinates only appear at most one time, so we can say, yes, this is a function. I'm hopeful that it is a pretty clear, cut and dry idea of determining whether or not your ordered pairs or your relation is a function. Take a look at part E. What may be helpful to all of you is to list each of these ordered pairs pertaining to the points on our graph, right? The other thing to consider is that we know that this will be a function as long as each x value only appears once. So let's take a look at this. My first ordered pair here is a -3, -3. My next ordered pair is a -2, 3. Next I have -1, 1. Then I have 1, 0. Next I have 3, 3. And lastly, I have 5, -1. As we scan this graph from left to right, notice that each x value is only represented at most one time. So yes, this is a function. Interestingly enough, we would know that this is not a function if any of these x values repeated. But what would that look like? So for instance, let's say that I had another point on this graph. Let's say that my other point is 5, 1. Now I'm going to hold my pen here because I don't want to mark our guided notes. I want to leave it as is, but I want you to pretend, I want you to visualize that I have a point right here. If I had another point right here, would you all agree that this is definitely not a function? It basically goes against the definition that we have on this page, where every x value has exactly one y value. If I had another point right here, I'm saying that 5 relates to both a -1 and a +1. So this fails the definition of being a function. If I had one more point right here, we would have to say, no, this relation is not a function. Good. Let's turn the page. Now, if we want to identify a function from a graph, we can use something called the vertical line test. So essentially what that means is we would be able to draw a vertical line anywhere on our relation, and as long as that vertical line hits that relation at most once, then we know we have a function. Can I go back to what I was just referencing on our previous page, where if I had a point here, where the tip of my pen is, if I had a point here and I drew a vertical line, do you see how it would hit it once and then twice? So this one vertical line would hit my relation in two separate places. If this vertical line hits your relation in more than one place, then it fails the vertical line test, meaning it is not a function. Our x value repeats. It is not a function. So let's take a look. For the first graph here, I can take any vertical line and I can draw it anywhere I want. Notice that here's my first vertical line. It hits the relation at one point. I can draw another vertical line. It hits the relation at one point. I can draw another vertical line over here. It hits the relation at one point. So wherever I draw my vertical line, it only hits my graph at one point. This is an easy way, instead of listing all of the points on our relation and then determining whether or not it's a function. Can you imagine listing all of the points on this particular relation? No, that would be crazy. Because we do have -3, 1, but we also have -2.9, comma, whatever that other value might be. That's going to be pretty crazy. So we use the vertical line test to visually check whether or not our graph is a function. So for our first one, yes, this passes the vertical line. I hope you don't mind me abbreviating VL. It passes the vertical line test, so it is a function. It passes the vertical line test, so it is a function. Let's take a look at this second graph over here to our right. So we have our circle. Now, I can pick any vertical line I want and place it wherever I would like on my relation. So for instance, let's say that I draw my vertical line here. If I draw my vertical line here, it seems like it's only hitting at one point. So we're thinking, okay, so far so good. But let's think about this logically. Take another vertical line, draw that through the relation, and it hits our relation in two separate points. We can draw another vertical line, another one, another one, another one, another one, wherever we'd like. And there are several points, there's an infinite number of points where it hits our graph in two places. So this fails, so no, this fails the vertical line test. So it is not a function. It's kind of cool that you can just look at a graph and say, oh, yep, not a function. Oh, yep, that's a function, right? And that's based on the idea of the vertical line test. Take 30 seconds and write out whether or not these two graphs are functions or not. Okay, let's take a look at our third graph. If you drew a vertical line anywhere here, you'll notice that it hits it at more than one place. So our vertical lines hit the relation in 2 places each, essentially, except for this last one. So this is not a function. For our fourth graph, if you draw a vertical line in any of these places, you'll notice that at most it only hits the relation 1 time. So we can say this is a function. Cool, right? It's as simple as that. Draw vertical lines. If it hits the relation at most 1 time, then you know that you're dealing with a function. If your vertical line hits the relation at more than 1 point, then it's definitely not a function. So let's continue with this idea. So when obtaining information from a function's graph, I want you to consider that the domain does not change. The domain is the set of all values, your x values, used as input to a relation. So think of domain as input. Look for all inputs on the x-axis that correspond to points on the graph. Your range is the set of all y values, or your output. So domain, input, range, output. Okay? Your range is your outputs on the y-axis that correspond to points on the graph. So same thing. Domain is x values, range is y values. But let's take it a step further. Think of domain as input and your range as output. Let's turn the page. Now, what I have up here is a quick recap of what we learned last unit when we discussed interval notation. Okay? We learned about interval notation being and I'm going to write this down at the top. So interval notation, we learned that interval notation has bounds, right? So we want to look at the left or the lower bound, and then we want to say what's the right or the upper bound. We noticed that when we had an open circle, that referred to a parentheses, but when we had a closed circle, that pertained to a bracket. So essentially, we have some sort of combination here, but we always go from left to right, or what I can consider smallest to largest. I think that might be very important to know, that your interval notation should always be smallest to largest. As you recall from our previous conversation, when we talked about the grades that you would need to get in order to receive an A in the class, you didn't say 100 to 90, you said 90 to 100. So order is incredibly important here. Every time you write interval notation, think logically. What's the smaller value? What's the larger value? Okay? Always think of the interval notation in terms of smallest to largest. So when we look at these graphs, it's going to be interesting in terms of deciding, well, what's the smallest value, what's the largest? And I want to show you how to navigate this. Let's take a look. So for example 3, we're going to use the graph of each relation to identify its domain and its range. We're going to write the domain and range in interval notation. That is incredibly important, interval notation. When we want to look at the domain of a graph, what you may want to consider, and I'm just going to jot some ideas down, if it helps, it helps. If it doesn't, that's okay. You know the definition of domain. When you think of domain on a graph, I want you to think how wide, right? And when you think how wide, you're always thinking in terms of your x value. So your x coordinates, how wide is this graph, right? What's the smallest x value? What's the largest x value? When you want to consider your range, at this point you want to think how low and how high. So you want to say what's the smallest value, what's the highest value. So you want to consider how low and then how high. I'm hopeful that that idea will be helpful in terms of determining what the range is, your lowest y value, your highest y value. So let me show you what this looks like with this first example here. Okay, we want to look at the domain. So we want to consider how wide this graph actually is, correct? So we start by following the graph as far left as we can. Okay, that actually might help for you to write down. You can say how left, how right. How far left, how far right. All of these things might be helpful. Jot down what resonates with you. So I'm going to follow this graph as far left as I possibly can. Notice I'm tracing this relation. By the way, is this relation a function or not? Vertical line. Notice it passes the vertical line test. So we definitely have a function here. So I'm looking at this function, and I'm going to follow it as far left as I possibly can go. Notice here I have an open circle, and this open circle corresponds to the x-coordinate -4. So my smallest value in my domain is a -4. And not only that, it's an open circle, so we're approaching -4, but we're not equal to -4. So that's how far left. Now I want to continue following this relation, this function, as right as I possibly can. So I'm following it right, and all of a sudden I hit an arrow. Well, we learned from last unit, when we have an arrow pointing to the right, we're essentially approaching infinity. So my highest value in my domain is going to be infinity. We also learned that we would not close infinity. You cannot use a bracket on infinity. You would use a parentheses to show that you are approaching infinity. Okay? Excellent. Now let's trace this relation again, or this function again. And when we think about the range, we want to think of how low, how high. So I want to go as low as I possibly can. Notice that here is the lowest my graph goes. Also notice that my y-coordinate pertaining to both of these points is a -2. So that's my lowest. But then you want to think, wait a second, is this an open circle or a closed circle? What I want you to consider is that because we have an open circle here, this takes precedence. So we're actually going to write parentheses here. Because there exists a value, right? There exists a value where -2 is not the y. So we're approaching that -2. So here, for our ordered pair -4, -2, we're approaching that point. We're not equal to that point. So because there exists this value, we're going to have open circle. I also want you to notice that even though you don't see closed circles here, all of these ordered pairs, all of these points on this line are closed. Every last one of these points are closed. Otherwise, you'd see a bunch of open circles. So we notice that the smallest value in our range is going to be an open circle on -2. Now I'm going to follow this graph and go as high as I possibly can. If I go as high as I possibly can, notice I've reached this arrow, which doesn't mean we end at 3. It means we continue on towards positive infinity. And there's my range. Let's do it again. This is going to take a little bit of practice, so let's do it again. Take a look at your second graph. We're going to start with the domain. So what we'll do is we'll follow this oscillating graph as far left as we can possibly go. So notice here that if I follow it as far left as I possibly go, these are actually arrows, even though they look like crap. These are arrows. So we're implying that we're going to continue on towards the left. And if we continue on towards the left, we have -1, -2, -3, -4, -5, -6, -7, all the way towards infinity. Now, I'm going to do the same thing, except I'm going to follow this graph to the right. Because remember, we're focused on the domain. So I'm going to follow this graph to the right, and notice I have another arrow. So we're going to continue on towards positive infinity. And there's our domain. Think of x as your input, right? And think of domain as all of your x values. So if we were to find several points on this oscillating graph, we would see that those x coordinates continue towards -infinity and positive infinity. Okay? Next, we want to discuss the range. Remember that range is how low, how high. So what I would urge you to do is I would urge you to follow this particular relation, which, by the way, is this a function or not? If you drew a vertical line anywhere through this relation, you would see that that vertical line hits it at most one time. So yes, this is a function. So back to the range. So I'm going to follow this, and I'm going to say, okay, wait, I have the same low point in every dip. And if I go to each of these low points, I notice that they each correspond to the y value of -1. This is a -1, this is a -1, this is a -1, this is a -1. Now, if you're trying to think, wait a second, is this an open or a closed circle? The only time it would be an open circle is if you visually see an open circle. Luckily for us, it's a solid line, so we are including that -1 value. Now, for our range, we want to see how high our particular function goes. So as I follow this oscillating graph, I can say, oh, wait a second, I'm going as high as a 1 as my y coordinate. So the highest or the greatest y coordinate, the y value we have, is a +1. Again, because there are no open circles, we know that we are including that 1 value in our interval, which means we need a bracket. Excellent. Please take 1 minute, don't overthink this, take 1 minute to find the domain and range for each of these two functions, starting now. Let's check it out and see what you all have. So, if we follow this graph, right, here's our function, we want to identify the domain first. So identifying the domain, as we discussed before, an easy way to think about this is to follow the graph as far left as you possibly can. Would you agree that if I follow this graph as left as I possibly can, I end up at this ordered pair here? Now, you're probably thinking of, wait, what does this actually refer to? Well, you know what this ordered pair is. This is the point 0, -4. So domain refers to x values. So the x coordinate at this point is 0. Because it's an open circle, we're going to use a parentheses to note that we're approaching that point, but we're not including that point. Next, we want to define how far right this function goes. And as we follow this as right as we possibly can, we hit an arrow, which means we're going to continue on towards positive infinity. And of course, you cannot close that. With the range, we want to go how low, how high. So again, we're going to follow this graph. Notice that this seems to be the lowest point. Let's continue. And so it in fact is the lowest point, but our lowest point is an open circle. So we're going to approach that -4. All right, so we're approaching that -4. Now we want to go as high as we possibly can. So we're going to trace this. If you stopped here, I would urge you to continue. If you continue tracing this line, you're going to pass that point as the highest and realize that this arrow implies that we're approaching positive infinity, in which case your range will go from -4 to positive infinity. For our last graph, we want to consider again the domain. It refers to all your x values. So trace this as far left as you possibly can. So you trace this as far left as you possibly can, and you have this arrow, which implies we are approaching negative infinity. As you follow this to the right, notice that it's continuing to grow in the direction to the right. So we're going towards positive infinity, and there's my domain. Your range is how low, how high. So we're going to follow this graph, and notice we have a low point here, but if I continue to trace this, I see that these values here are lower than my value in this part, or this part of the function, the graph. So if I continued, I notice I fall towards negative infinity. Parentheses around that, and then trace this and go as high as you can. You might hit this peak here, but remember, if you continue to trace it, these values, these y coordinates, are higher, they're greater than the y coordinate here at this peak. So you follow it and you notice, wait a second, my largest value is going to be positive infinity. So both the domain and the range represent all real numbers. Okay? Good. And actually, I'm going to make a note of that. All real numbers. Just something to think about as you're looking at domain and range when they include all of the values that you have in existence, but all real numbers. Let's turn the page. Okay, so functions as equations. Functions are often given in terms of equations rather than as sets of ordered pairs, tables, or graphs. So the independent variable is something that we have to consider along with the dependent variable. What I want to do is I want to flip back just to kind of talk to you about input and output. So recall on page 3, we had written here that the domain is the set of all values, x values, used as input to a relation. When you think of the domain being your input, I also want you to relate the idea of input and independent. Okay? So when you think of your input, I want you to think of independent. Domain, x values, input, independent variable. Your range is your output. So essentially your range, those values depend on y. So since, on x. So since the output, y, depends on x, I want you to consider that the output represents the dependent variable, where y depends on x. X input independent, y output dependent. Hopefully that's helpful in terms of organizing your thoughts and how to organize these ideas. I always like saying things like this out loud and kind of making this expression very clear in our minds. Domain represents the input, which is our independent variable. Input, independent. Range represents our output, output, dependent variable. Okay? And we know that domain is x values and your range is your y values. In terms of kind of describing the independent variable and dependent variable using this statement, I want you to, let's start with the dependent variable. So the dependent variable basically says that the value is blank using a value for the independent variable. So essentially what you would consider is that if y depends on x, then the value is calculated using a value for the independent variable. And I can show you what I mean by that briefly by taking a look at, for instance, linear equations that we've seen from Unit 4. But the independent variable, I want you to think of that as the value is assigned from any value assigned to the domain. So it's essentially, and I know it's kind of like I'm repeating myself, but the independent variable is chosen. And you know what? That's a better word. The value is chosen from any value assigned to the domain. So let me show you what I mean by this. Let's take the equation y is equal to 2x minus 7. You all know how to graph this. You know that your slope is a positive 2. You know that your y-intercept is 0, negative 7. You know this. You know how to graph that particular equation. What we talked about briefly from Unit 4 was how to graph this by plotting points. So for instance, let's say that I wanted to have a table of ordered pairs that pertain to that line. What I would say is, okay, let's come up with 3x values. So we're going to choose any 3x values. So how about we choose negative 1, 0, and 1. We know that we only need 2 points to make a line, but I would like to play around with this, and I want to choose any 3 x coordinates in my domain so that we can determine what their corresponding y values are. So if my first x value is -1, my input, I would input -1 for x. So take a look. When x is -1, I'm going to input -1 in place of x, and I'm going to calculate my y value based on that input. So y is equal to 2 times -1, which is -2, minus 7, which means y is -9. So for my first ordered pair, I know that a point on this line is -1, -9. Again, if it helps, you can write it out as an ordered pair. Let's do it again when x is 0, when my input is 0. So when x is 0, we have y is equal to 2 times 0 minus 7. That cancels, right? 2 times 0 is 0, and 0 minus 7 is -7. So my next ordered pair is 0, -7. In other words, when my input is 0, my output is -7. Input, output. When my input is 1, my output is -5. And you can verify that on your own. Okay? Input, output. Independent, dependent. Y depends on x. I hope that's clear. We're now ready to move into something called function notation. What I want you to consider is that in our equation y is equal to 2x minus 7, we would actually replace the y with f of x. And what that means, and I'm going to replace the y with f of x. See how I took the y out and I replaced it with an f of x? But the rest of the equation is going to stay exactly the same. So here's what this means. F of x basically notes that this is a function of x, right? So this is a function of x. X is our input, and after we plug in our input, the value that we get is our output, and our output refers to f of x, which is y. So for instance, I'm going to showcase exactly what we did here, but using function notation. Let's say I wanted to go back to my input of 1. So if I wanted to say, what is the value of this function when x is 1? Notice I'm replacing x with 1. You would say, oh, okay, that just means I have to replace every x with a 1. And if I replace every x with a 1, I get 2 times 1, which is 2, minus 7, which is -5. Do you see what just happened? All I did was I replaced my x with 1. So I'm finding the value of f of 1 in this case, which is the same as finding the value of y when x is 1. Input, output. Input, output. Notice this does not mean f times 1. This is not where you divide by 1 and you solve for f. No, no, no. This is function notation. So it's a fancy way of saying I have a function and now I can state that it's a function of x since x is my input, and I can plug in values for x and solve for that output, f of that input. Okay, so in this case, f of 1 is -5. That refers to the ordered pair 1, -5. X, y. Okay, it's just a fancy way of saying it. Okay, so let's explore a little bit more. Take a look at example 1. We want to find f of -2, and we also want to find f of 3. So we're going to do that in each of these graphs. So I want you to focus only on our first graph. I want you to recall that our inputs are x and our outputs are y. So if we are looking at f of x and the first expression says f of -2, then I want you to consider that we want to find the value of y when x is negative 2. So we go to our chart, our graph, and we go to where x is negative 2, so negative 1, negative 2, and then we find a point corresponding to when x is negative 2, and it's right here. So this ordered pair is negative 2, negative 1. What that means is the value of f of negative 2 is equal to negative 1. Not bad, right? Let's do it again. This time we want f of 3. So again, think of x as 3. So you go to 3, 1, 2, 3. And here you have to find the point corresponding to when x is 3. So that's this point right here. So if I were to write out this ordered pair, that would be 3, 2. So when the function is evaluated at 3, when x is 3, y is 2. And that's the solution. That is how you write function notation. This is how you use it. This is what it means, how it breaks down. Let's do it again. We still want to find f of negative 2. So again, notice we have our line here. It's a linear equation. I want to go to where x is negative 2. So negative 1, negative 2 right here. According to our graph, this point here is a negative 2, 0. So when x is negative 2, my corresponding y value is 0. This is a function, so that's why we're able to say f of negative 2 equals 0. It has one specific value at that point. Similarly, we want to find f of 3. So we're going to go over to where x is 3, so 1, 2, 3. And what we'll do is we'll go up until we hit the line. So we know that when x is 3, 1, 2, 3, 4, 5, our y value, our corresponding y value, is 5. And that's all you have to do to identify specific points. When you're given the input of 3, according to this graph, our output is 5. Good, let's keep going. Let's keep working on this idea. Number 4, we want to evaluate the following functions for the given inputs. We are given the function f of x is equal to 3x plus 2. The first thing I want to do is identify the solution to f of negative 6. So I'm going to write f of negative 6 directly below my f of x here. The reason I wanted to write this directly below is because I wanted us to notice that the only thing that changed from this expression f of x to this expression f of negative 6 was that x became negative 6. Is that clear to everyone? X became a negative 6. So anywhere you see an x, it's going to become a negative 6. So we have f of negative 6 is equal to 3 times negative 6 plus 2. Now let's do the math. F of negative 6 is equal to 3 times the negative 6 is negative 18. And negative 18 plus 2 is negative 16. So what this implies is that when x is negative 6, our corresponding y value is negative 16. When our input is negative 6, our output is negative 16. When our independent variable has a value of negative 6, our dependent variable has a value of negative 16. I'm hopeful that by me using the different terminology that you're understanding how all of this plays together. Now notice the follow-up question. For what value of x does f of x equal 14? I want you to notice that this time we are not given x. So it would not make sense to replace x with 14. That would be false. What we would consider is if I rewrite this equation, our function, f of x is equal to 3x plus 2, we would note that we do not know x. What we do know is that f of x is 14. So this part right here, the f of x is 14. So we replace f of x with 14. We rewrite the rest of the equation, equals 3x plus 2, and then we solve. First things first, I'm going to subtract 2. We have 12 is equal to 3x, and then I'm going to divide by 3. So I get that 4 is equal to x. So for what value of x does f of x equal 14? That would be 4. In which case, this refers to the ordered pair 4 comma 14. Okay? If we saw this visually on a graph, f of x equals 3x plus 2, this is a linear equation. I'm going to draw a small graph just to show you what this looks like, just to remind you of what this looks like. Here's our x-axis, our y-axis. We notice that if we have f of x is equal to 3x plus 2, my slope is 3. My y-intercept is 0, 2. So you would go to 0, 2 and plot your first point, and then you would apply the slope. The slope says you're going to go up 3 units, 1, 2, 3, and then over 1. Okay? And then you'll go up 3 units again, and then over 1. We're going to connect these with a straight line, and that's what my graph looks like. So this is definitely a function. Here is the line f of x equals 3x plus 2. Or in other words, here's the line y equals 3x plus 2. When x is 4, y is 14. When x is negative 6, y is negative 16. Does that make sense? Okay. Let's do part B. F of x is equal to negative 3x plus 22. You are responsible for finding f of 8. And then, for what value of x does f of x equal 40? When you have your result, please share in the live chat. How about 3 minutes starting now? Excellent. We have some answers coming in, so let's check this out. So we want to find f of 8. And essentially what we learned is that means that the x is going to be replaced by 8. So wherever we see an x, we replace it with 8. Let's go ahead and do the math. F of 8 is equal to negative 3 times 8 is a negative 24. Plus 22 implies that f of 8 is equal to negative 2. Excellent. Brittany, Michelle, that was perfect. So this corresponds to the ordered pair 8, negative 2. Now I do want to point out that if the question asks find f of 8, your answer would be right here. This would be the solution. F of 8 equals negative 2 is the solution. What that implies is that 8, negative 2 is a point on that function. Okay? Next, for what value of x does f of x equal 40? So again, I would simply rewrite the problem. It's going to be helpful. And we know f of x is 40, so we replace f of x with 40 altogether. And now we solve. So we're going to subtract 22 from both sides. Notice that gives me 40 take away 22 is 18. We have 18 is equal to negative 3x, divide by negative 3, and you find that negative 6 is x. So wonderful. Again, Brittany, Michelle, Nicole, excellent, excellent, excellent job. That is correct. When f of x is 40, x is negative 6. So when y is 40, x is negative 6. So the interpretation is that negative 6 comma 40 is a point on that function, on that line. Okay? So just to clarify, here's my first answer. Here's my second answer. Beautiful. Now check out part C. We have f of x is equal to negative 2x squared plus 4x minus 3. We want to find f of 5 and we want to find f of negative 7. What I'm hopeful from the conversations we've had so far is that if you wanted to identify what f of 5 is, you would say, well, if x gets replaced by 5, then that means anywhere we see an x, we will replace it with a 5. And that is correct. So we would write -2, and instead of x, we would replace it with a 5, but remember it's being squared. So I want to make sure I write the square there. Then we have plus 4 times x, but x is 5, so we replace it again. And then we have minus 3. So we have f of x equals -2x squared plus 4x minus 3. Bam. This is exactly the same, with the exception of we're inputting our 5. Our value for the independent variable is 5. And now we just do the math. So we have f of 5 is equal to, remember the order of operations. This first term reads -2 times 5 squared times and squared. Out of times and squared, which one comes first? Squared. Think PEMDAS. Okay? Think the order of operations, PEMDAS. So we have to square the 5 first. So we have -2 times 25 plus, and I'm just going to write out the rest. We can do this step by step, no big deal. Next, let's simplify. -2 times 25 is -50. 4 times 5 is 20, minus 3. So now we just have to move from left to right. So -50 plus 20 is a -30, and -30 minus 3 is -33. So f of 5 is a -33. Okay. In this case, we're looking at a quadratic function. It is no longer linear. This is a linear function. Part A was also a linear function. Part C, because my highest power is a 2, that implies it's a quadratic function. So when your degree is 2, it's a quadratic function. This still can be interpreted, or should be interpreted, as the point 5 and -33. That ordered pair, that 0.5 -33, is on that parabola. So it belongs to that quadratic function. Okay. Let's do it again. We want f of -7. So f of -7 is equal to -2 times, use parentheses. Parentheses is going to be super important. -7 squared plus 4 times -7 minus 3. Okay. Anywhere you saw an x, you replaced it with a -7. Now let's do the math. F of -7 equals, we want to square that -7 first. So we have -2 times positive 49. A -7 times a -7 is a positive 49. Plus 4 times a -7 minus 3. Let's continue. We have -2 times 49. If you take -2 and you multiply by 49, you'll get a -98. A positive 4 times a -7, that's a -28, or -28 minus 28. We know these are separate terms. First term, second term, third term. Next, we simply want to move from left to right. So -98 minus 28 minus 3. That gives us an answer of -129. So that is your solution. Again, this implies that the point -7, -129 is somewhere on that graph. It's somewhere on that parabola. Okay? And just for your reference, this parabola actually looks like that. It's an upside down U. That's because our leading term is negative, so it's concave downwards. If our leading term was positive, it would be concave upwards. It would be like a smile as opposed to a frown. Very nice. Okay, on that note, we've gone as far as we should go for the day. Okay, that's a lot of material. You have domain and range. You have the vertical line test to determine whether or not your relation is a function. You also learned about function notation and how to evaluate at a given point. So I want you to use all of that information and to kind of think about everything that we covered today and practice this in your Lumen homework to ensure that you are in fact mastering the material that we've covered. Excellent. Wonderful job today. That was phenomenal. Thank you for participating in the live chat. And I look forward to seeing you all on Thursday. Luckily, I would imagine we'll probably finish this Thursday. If not, then we'll go into next Tuesday. We still have a week and a half left of classes. All right. I will see you all on Thursday. Please stay safe. Please stay healthy and have fun. Bye.